Hi, I'm Chris with Sanderson Test Prep, and in this video we're going to take a look at drawing Lewis dot structures. So let's get to it. So for our first example, we'll draw the Lewis dot structure for carbon dioxide. And the way that we are going to draw Lewis dot structure, so the first step is we want to count the total number of valence electrons for all of the elements involved. So here we have carbon. That has a valence of 4, and then oxygen that has a valence of 6, and there are 2 of those oxygens. So if we add all of those together, 4 valence on the carbon, the 6 valence on the 2 oxygens, that's 12 and 4 together gives us 16 valence electrons. So that's step 1, is to make sure we know how many valence electrons we're dealing with. Now for step 2, we're going to draw what sometimes is referred to as the skeleton structure, but basically you take the elements that you have here, the carbon followed by the O2. So the element that's by itself, the carbon in this case, is going to act as your central atom. So we're going to have a carbon, and it's going to be attached to 2 oxygens. So this is our skeleton structure. We don't know if this is the correct bonding, and we haven't yet added in any of the lone pair electrons. But this is our skeleton structure. And then from here, what we want to do is try to fill the octets for each atom, and we want to evaluate something called the formal charge on each atom as we go. So let's take a look at how this would work. So you could start just by adding in lone pairs everywhere. So on the oxygens, oxygen has a valence of 6, and it has the potential of sharing a total of 8 electrons. So you're going to have the 2 in the bond, and then that means there would be 6 other electrons as lone pairs. So we go 1, 2, 3, 4, 5, 6. So that together with these 2 electrons in here, in this bond, right, there are 2 electrons in that bond, so that oxygen would have a filled octet with 8 around it. And if we did the same thing over here with this oxygen, it would look something like this. And if we did the same thing with the carbon's sharing 4 electrons from the bond, so then we would have 2 lone pairs around the carbon. So let's see how we're doing in terms of our total numbers of electrons that we see. And if we go to count this up, we could see 2, 4, and I'm going to highlight as I go just to make it a little bit easier to see. But we would count this as 2, 4 for the electrons in those bonds. And then if we count each of the lone pairs, so that's 6, 8, 10, 12, 14, 16, 20, 22. So we can see that this would be way over where we want to be, right? We're supposed to have only 16 electrons shown in this Lewis dot structure. So when you come up with a number like this that's way over, then that means that you need to somehow increase the amount of bonding electrons that you have and decrease the lone pairs. Now, why does that work? Well, because if you have electrons in a bond, then that means that it's being shared by 2 of the elements. So for example here, if we took out this lone pair from carbon and this lone pair for oxygen, so we took out 4 lone pair electrons, and if we replace it with an additional bond with the oxygen, so now those 4 electrons, because they're being shared in a bond, it's only 2 electrons in the bond. So that helps get us closer to our value of 16. So let's test this out and see how we're doing. So here, if we count again, for the bonds we go 2, 4, 6, and then we count the lone pairs 8, 10, 12, 14, 16, 18. So we're a little closer, but we're still over. So that means we want to add to the bonding a little bit more. So here, if we take out this lone pair from oxygen and this lone pair from carbon, and then replace it with a bond, now let's check how we're doing. So we have in the bonds 2, 4, 6, 8, and then 10, 12, 14, 16. So this checks out. And that would be the correct Lewis dot structure for CO2. Now let's take a look at an example that's a little bit more complicated. So here we have a nitrate ion. So we have NO3. And first step, I'm going to count the valence electrons. So nitrogen has 5. and then the oxygens have 6 each. There are 3 of those. And then here we have something unique because it has a charge. And so if something has a positive charge, that means you would take away one of those electrons. If something has a negative charge, that means you have an extra electron there. So because of that negative charge, we're adding 1. So this plus 1 is going to be added to our total valence count. And our total valence count in this case will be 5 plus 18, which is 23 plus 1, 24 valence electrons. Okay, so now we're going to start with nitrogen as our central atom and shift this up a tiny bit. So we're going to have that nitrogen bonded to these 3 oxygens. And let's start placing our electrons and doing a little bit of counting. So here we have our lone pairs on these oxygens. And we're going to have 1 lone pair on the nitrogen to fill the octets for everybody. All right, time to do a little counting and see how we're doing compared to that number of 24. So right now we've got 2, 4, 6 for the bonded electrons, and then we have 8 for the lone pair on nitrogen, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, so we're over by a little bit, which means we have to add to our bonding. So let's see if we can add to our bonding here and see if that helps. So let's start with the lone pair on the nitrogen and one of the oxygens. Doesn't matter which. All right, so now if we create something like this, let's double check where we are on this. So we have, for this one, a 2, 4, 6, 8 count around the nitrogen for the bonded electrons. And then we'll count the rest of our lone pairs. 2, 4, 6, or sorry, let me count from our value of 8. So 10, 12, 14, 16, 18, 20, 22, 24. So now we have 24. And so we know that this is matching our valence number of electrons here. Let's see how we could evaluate this looking at it from a charge perspective. So this is another topic that will be introduced when you start learning Lewis structures. You're also going to learn formal charge. And formal charge has to do with the charge in each individual element. Let's check and make sure that this molecule as a whole has a negative total charge. And the way you do that is you look at the valence electrons for each individual element. So oxygen we know is 6. If we look what surrounds the oxygen, here we have 2, 4, 6 for the lone pairs, and then oxygen is going to claim 1 of these 2 electrons in the bond. So each bond that has 2 electrons in it, 1 will be claimed by each element sharing those electrons. So here this would be 7 electrons, and for a valence of 6, that means you have 1 extra electron. So this would be a -1 for the formal charge on that oxygen. Let's take a look at this oxygen. Here we have 2, 4 for the valence electron, or for the lone pair electrons, and then we have these 2 bonded electrons. So that's 2, 4, 6. That's a formal charge of 0. We like that. We want to minimize formal charge where we can. All right, let's check this oxygen. And as you can see, it has the same lone pair configuration as the other one. So even without counting, we already know that this is going to be a -1. So that would be a total of -2 for the element as a whole. Let's check the nitrogen. Nitrogen has a valence of 5, and it claims 1 of these bonded electrons in each bond. So that would be 1, 2, 3, 4. So for nitrogen with a valence of 5 and 4 electrons, that means that it's 1 electron shy, which means this would have a +1 charge. And so if you add up all those formal charges, you can see that this molecule as a whole would have a net charge of -1. And that matches the charge that we see here. So when drawing Lewis dot structures, you want to make sure that the valence number of electrons works out. But if you have a more complex molecule, you can also use formal charge to figure out what that preferred structure is going to look like by figuring out the bonding that will minimize the formal charge. So both things are happening at the same time. We're trying to minimize formal charge and achieve our desired number of valence electrons in drawing out the molecule as a whole. For more, please check out our other videos, and thanks for watching.